Okay, thank you for being here for the lecture of today. Yeah, let me restart very quickly, considering the example of last time, because do you remember I told you the idea is to show you also uh, the simulation of this emulation method, and then we will go ahead with the rest of the material. Let me see if I am able to switch on the lateral camera. Probably no. Mhm. Why now it doesn't work? 1 second here. Yeah, probably now. Let me see. It doesn't work. Uh, no, 1 second. I didn't connect clearly. Now, exactly. Look, again, emulation means that we realize the controller in continuous. For instance, given this example, this system, extremely easy, I don't want to say. It's an example, no? 1 divided s squared, and double integrator. It's not so easy in the sense it seems to be easy, extremely compact, but it's in double integrator. And double integrator is in a system which is unstable. I don't know if you remember, if you put an initial condition, the back transformation, Laplace transformation is in the ramp. Uh, just this is something which uh, recalls us that is a system which must be stabilized. Anyway, we have the system here. We do everything as we learned in automation on some of my courses, and we are satisfied, assuming that we are satisfied with this uh, controller. This means this controller satisfies our specifications, in particular the stability, but not only. Then the emulation is characterized, as I told you last time. I demonstrated, let me say, uh, uh, by, let me say, substitute or plug in S equals Z minus 1 divided T. Do you remember I told you why this? No? This forward Euler approximation. This means I will approximate this controller here using this approximation. I told you how let me say where let me say so where this approximation come from. Basically, is circa, but anyway, if we want to approximate it in the controller, we say equals. Anyway, plugging in, we'll have this expression here as the function of t. As I told you, t, sample time, is something which is not irrelevant. The choice of t, extremely important, because also looking here, we realize not only the zeros of this transfer function. This is the transfer function in z. Do you remember? Until now, z is the variable which I define the variable z as in a pragmatic form. This delay, the shifting operator. We will see that z has also another meaning. It's a very deep mathematical meaning. We can see also from here, which is related to the s, which is a complex variable. But anyway, let me tell you about this aspect later. Look here, depending of the change, not only the zero. About the zero, it's quite abstract to understand what the zero is. It could be that I can tell you a little bit about the root locus. I don't know if I told you somewhere, but in particular the denominator. If you remember in S, at least in S means in Laplace domain, the denominator of a transfer function is responsible for the stability. Here is the same, but also the zero. It could be, in any case, I will tell you in discrete a little bit, but it could be that, and I will tell you about the root locus so we can understand a little bit better how T is extremely important for the stability and not only, also for the, let me say, for the performance. In fact, you remember last time, I will come back on this, uh, I told you that it seems that for T very small, we have a better performance, but this is a little bit not totally correct. I mean, we have a better representation of the signals, but not necessarily a better performance. Let me show you what we have seen last time. At the end, I don't find now. Yeah, look, this is the general discretized control law. If T very small, theoretically infinite small, zero, in order to represent in the best way, apparently, not apparently, if T is very small, you remember the signals can be represented very well. But look what happens at the controller. For T small, very small, theoretically zero, we have a UK equal UK minus 1, because this part here, the feedback, let me say, cancelled. Do you remember this concept here? 3AK minus 3AK, 0. This means we have UK equal UK minus 1. We annihilated the controller. This means the system is not controllable. Of course, in terms of representation of the static representation of the signal, if you have a TS simple time or the T very small, the signal is represented very well. I don't know if you remember, no? You have a continuous signal. If the stepwise approximation is realized with very small T or the TS, it's clear that I will approximate very well the signal. But what happens dynamically? We can see directly here. I annihilate the controller. The controller doesn't work because I have a UK equal UK minus 1, because here T is almost 0. Let me say 0 in order to understand conceptually. And here is 0 because for T equals 0, we have a 3E minus 3E. This means the feedback is not there, because the feedback came from the error. No? The error is what I want minus what I have. Let me show you now the simulation. Look, here we have the Doppel integrator, which must be controlled. With this controller, it came from our continuous method. If you remember in automation, I don't know in which course I told you this possible methods, but in any case, root locus, I think I didn't do in this automation last semester. But anyway, assuming that somebody say this is the controller that until now worked, we realize this controller in continuous form with operational amplifiers, circuits, and so on. And then we want to transform, or we want to realize this controller here. The controller is this here, no? And it's exactly what I told you, what we have in the lecture. 0,2, and which multiply this. And look, what we have here is exactly what I told you until now, but with T equal 1, I think. Let me see. Yeah, with T equal 1. This means I realized here, not this is in the general controller, that works for each T. I leave you as an example at home. No, try to realize in Simulink, this here, this controller here with the general T. It is easy as example, I think. No. Now I collapses in a particular form for T equal 1. Nils, you will have in my study, but anyway, you can write. No? I upload everything. everything in one folder, nevertheless. No, so let me say the material. What I implemented is this, which is obtained, the scheme from t equal 1. Why that? Didactically. But of course, should be nice. I don't have time here, but it's easy for you to test with different t. You will realize, for t very small, the system is not controllable. I have told you here. The reason is here. Try to do at home. This could be also a nice example in order to have a feeling about that. It seems to be better. Of course, it's better if I have to approximate statically in the signal. I don't know if you understand what I intend with statically. Let me write for you. Second. Statically means, assume that I have a signal, a continuous signal. Of course, if I consider, you remember this, a very large, or a large t, I have a very, let me say, or an approximation is, again, t, no? Which is this one. If I compare, let me see, I have another column. Okay, no. If I will compare with this, let me say something like that. No? It's clear, no? Let me go ahead a little bit quickly, that the red approximation, which consider the t red smaller than t, is a better approximation, but just statically. If this approximation is inside the control loop, we can see from here. Thus, we annihilate the control. Now, try to do at home with different t. I can look if I have, but I think you can realize easily. Basically, this should be excuse me. This control here should be realized in terms of yeah, considering a t. I can look if I have one, but it's easy to do. Should I do for you? No. Or, what is here is again very important. Very important is the element uh, one divided set, because here we will realize. Let me show you what I intend. One divided z is exactly what I told you until now. This is shifting parameter z up to -1. We can see here, I add 3 divided 5, multiply the error. This element here is in a sample and hold. Basically, here I have a continuous signal. And here I will realize basically exactly what I told you now with the approximation of a signal. Plus or the minus 2 divided 5 multiply a error but of k minus 1. Let me see. Try 3 divided 5 multiply a of k, not delayed, minus 1 divided 5 multiply e delayed. It's exactly the controller, but please pay attention, t equal 1. Where is t is here. Simple time. Let me show you now the results. We have this as results. Now, could be a nice project at the beginning to test with smaller t. I suppose with smaller t will increase a little bit the precision, but smaller and smaller will not be there. I mean, I am thinking, I'm sure that we have an optimal t, because t, you remember I told you last time, t very small, we have seen that cannot work. Microsecond, nanosecond, I don't know, it depends of the dynamics, but there is an upper bound. Under this upper bound doesn't work. I mean, we realize that the system does not react. I show you mathematically. This means I cannot follow the blue, the yellow line with the blue line. Also, for large and large t, nevertheless, I have the bad approximation of the signal in this case. This means we can see that the both aspect plays a role approximate of the signal, and nevertheless the controllability in this case here. This could be a nice project starting from here to think how I can calculate the optimal t. PSO, Kalman-Fritte, you don't know it. No? Okay, but PSO, you know. We did in the other course, no? Yeah. But also in this course, remember at the beginning, two students that now they started with the project because at the beginning the idea was not to tell you that the PSO, because PSO is also included in different courses, but nevertheless makes sense because in a discrete method in any case, and could be integrated here, for instance, or in look at this. If I don't know if I have, would be nice if I find directly with the general T, otherwise I can also implement, but let me look if I find, because we need time a little bit. Let me do it. Let me do it. I need a few minutes. Look. I copy this. This could be also an impossible project. Too easy, no? But if you integrate PSO, we can conceive a little bit the problem together. Because I would like to show you this. I need 5 minutes. Let me save with another name. I modify just this. Save as, no? Why doesn't work? Now. Let me say emulated system for each t. Okay.
Das lädst du hoch, oder? Kannst du das hochladen?
Yeah. I will upload everything. Let me see, because once I tested also without this, but we have some problems. I don't remember which one. Okay, now I copied. Let me come back. Let me come back. Excuse me, with Zoom. Yeah. How I have to realize is this now. Let me. This expression here is a function of t. This means 1 minus t u of k minus 1. Let me go here. Uh, yeah, here is absolute is not here. This means I need another plus. Mhm. And this means I need to consider this. Apply. Let me do it. This is u of k. U of k. And then I have to consider u of k minus 1. It is this one. It is better if I do, probably, no? Did you agree? This is the shifting which realize the delay of uk. This is uk. No? And here I have to multiply by 1 minus t. This means, let me copy this, for instance. Now it's better if I do, probably. You can improve a little bit the form. Invert. And now here inside, I will write 1 minus t. Basically, if I have a u of k, here I have a u of k minus 1. U of k minus 1 is multiply y minus t in order to realize what? This here. Now, this here is enough to modify what I have. What I have. Look at this. This means I have to go here, and here, or we have 3 divided 5 multiplied a k does not change. I show you. This element does not change. 3 divided 5 of e of k. I have just to modify this. Let me show you. It is difficult a little bit, but this means I have multiply by t minus 3. If you want, I can include also here. No? Yeah. By t minus 3. This means t minus 3. I think should be enough. Let me check together with you. Here we have e of k. Here we have e of k minus 1. Let me write. After notation. After the discretization, I have a of k minus 1. A of k, excuse me. The discretization I need because I have a continuous signal and a continuous signal. After the integral, you have a of k. Here I have a of k minus 1 in accordance with the shifting element. And here I multiply t minus 3. Let me see if I forgot something. Yeah, I forgot. No, excuse me. I forgot to divide by 5, no? But it's not a big problem. This I realize this, but I have to divide by 5. This means here I have to consider divided 5. Mills, did you agree? No? Laura. Here, why is 3 divided 5? 3 divided 5 multiply e of k should realize this. without t. This does not depend of t. Okay, now look what happens. If I put t equal 1, let me write also inside here t, because let me show you to everybody. It was 1 because the first example was t fixed equal 1. Here the simple time. I have to put t here, I have to put t also in z up to -1. Because also this is in a shift. I don't know if it's clear the difference between 0 or the old. This is sample and hold. You know, sample and hold, Andreas probably told you about. Sample and hold. In German, I don't know. I take a value and then maintain the value for t time. And this means at the beginning was 1 second, and now it's t, we can change. I have to change here, but in the meantime, let me show you. I have to change also here, because the sample and hold at the same time should be held, or that should be held, excuse me, for the same time, or let me say, the system is delayed with the same time. This means I have to put here t. Okay, let me put now in MATLAB t equal 1 should be exactly the same as before. And then we will try for a different value, and we can conceive a possible project, including, for instance, PSO, which we find an optimal t. Let me see if we have the result as before, more or less. Should be. Yeah, it is better to look at the comparison. Yeah, you can see the same result. Now, let me go directly in MATLAB without sharing. Write t equals 0,5. Look what happens. For t equals 0,5, we have something like that. Unstable. Interesting. Is already in a critical situation in which it seems to be that the controller is not more, is not working anymore. Of course, is in a particular case in which I put some round value, 2, 3, 1 divided at square is in a critical, yeah. Let me reduce this example I took for a book. Let me consider 0, I don't know, 8. Let me see. I don't know if it's better. We cannot see the difference, no? Not so much. We have to put an indicator, probably. Let me consider the error square integral. In order to realize how this minus this squared integral. And then I put in scope display, better. Stay on scope. Try to do at home to improve a little bit. Yeah, let me see. With 0,8, we have the error square equal 0,3383. Let me come back to t equal 1 in order to see if we have a differences. Zero, 3383. Yeah, it seems to be, look, stand this way up here, that 1 is better than 0,8. This means we have to increase a little bit t in order to look when this will increase, in order to see if we have the possibility to find the t optimal and which direction. It seems to be that the direction to increase. Now, of course, the example is a little bit artificial. No? 1 divided square is, therefore, we have this strange number. But if you have a real system with in this case particular number, not one, so of course, what I told you about an optimal. Anyway, we can see that reducing t, we have in a worst situation because the error was 0,33. Let me increase t. Now, what I expected, increasing t, will be worse than not immediately, but somewhere, let me see, 1,5. Now, with 1 is 0,2, 5, 4. Let me see. You can see. This means we have a convex region. You understand what I intend? Basically, this error, the error squared of the approximation, as a function of t, they have a minimum between t and t,5, right? I remember when, because it was 0,22, right? With t equal 1. I don't remember. I didn't. With t equal 1, the error square integral was, okay, 2, 4. It doesn't matter. In any case, between 1 and 1,5, of course, we can, better to say, between 0,8 and 1,5, we have somewhere in sense of time and a minimum. This could be a nice project. I don't want to apply on this. We can at the beginning test on this to think about to look in integrate the PSO in this kind of system directly on this. I have already some prepared file which combine PSO, my PSO in Simulink. I don't have time to tell you in the lecture, but I can give you, if you want to go on this integration PSO with discrete system, not necessarily on this topic here, we will see next topics, but this could be a nice example, a nice, yeah, as I would like to say, it's a nice exercise, not only for the exam. Okay, let me now go more in depth on this aspect of the discretization, but I think it was interesting also to look at this example. No? At least we have also a possible formulation for a problem, but of course I would like to consider exactly the system which we have in order to have something more interesting, I would like to say, because here with this 1 divided a square, but in any case, what I told you is confirmed, is validated. For smaller t, the control does not work. Do you remember? Because u of k equal u of k minus 1 means that the control doesn't work because it's not updated. Independently what happens in the error. Cannot realize anything. And we have seen that for reducing t, the control does not work. Does not work means for 0,8 we have a bad performance, and reducing we have also the system become unstable, as if really the control is not there. Increasing t, of course, depends how much. This means in between we have an optimal t. This could be also in a practical example, more practical project, let me say, interesting to integrate in a system as PSO, which belongs to our codes. Okay, let me introduce the topic of next week. Next week I am here, no problem. If you are here, we can, let me now share. I introduce in this a few minutes the topic of next week. Now we will see, excuse me. I will introduce forward error, backward error. Do you remember I told you that for Euler we have two methods. About that, probably I already introduced a little bit this. Explicit means, if I consider forward Euler, means that x of k, this means after the discretization of a differential equation, I have f of x of k minus 1 and u of k minus 1. This means the function, or the system, when discretized, appear in this form here. It is an explicit form. What is explicit form? Means that the state at time k multiply t, no, we know what we intend, is the function of the previous state and the previous input. What happens if I apply backward or any kind of implicit method? We have seen that we have an implicit method in Runge-Kutta. Probably you heard about that. Anyway, we have other different implicit method. Probably you learn in technical mechanics, implicit Runge-Kutta methods, something like that. But anyway, think that it's not only backward Euler and the implicit form, which means that xk, you have also other methods. Xk is in a function. Once we have the discretization of xk, please, here is the big difference. Of x minus 1 was present also in forward Euler. Forward is implicit. Backward is, excuse me, forward is explicit. Backward is implicit. Basically, I summarize here again. U of k, which was not present here, and u of k minus 1. But the critical point here, the critical element in this method, again, backward Euler, which generates implicit form of the differential equation, is exactly the presence of this here. Why that? Because to realize the dynamical model, or to realize the model which reflect the presence as a function of the past, here is not possible. Because xk depends on xk. Do you remember in high school? If I have to isolate xk, I have to be able to put this xk on the left part. Here it seems to be not necessarily always possible. It's in a form of not causality, because what happens today depends of what happens today and the rest. For uk is not a problem, because uk is the input. The problem is for xk. This I have it. Because you remember in forward Euler, also in Simulink, if you look in Simulink, the input is delayed u of k minus 1. I don't know if it's I don't know where it's, but this really is not a problem. The problem is this one, because I cannot explicitly write x of k as a function of what happens before. As a form of not causal. No? Okay, let me show you. You have to get. You have to go next week. 1 minute, yeah. The controller is basically something similar, because in any case, I need, because controller is a system, something like that, or something like that. If uk depends on uk, I cannot realize the controller. I need something like that or something like that for the control. This is important, this consideration. Yes, in a general system, but basically, yeah, we will see that I need this if the controller is model-based. In our situation, if you look what I did today, I need something like that. Because if UK is appear here, we don't have any causal system, control in this sense, no? System as control, because UK depends of itself. Okay, next week, we will look a little bit more in depth on this. And then I think we can do some important consideration and also formulate all the problems in this context. Thank you for attending this lecture. We will see next week.